is great. So I'm Chris from NASA Global Modeling and Assimilation Office. And this presentation is not mine, actually. This is authored by Emma Nolan, who couldn't be here. Essentially, Emma is leading a project that's under the theme of bridging the gap among different SAGE instruments. As we know, we had a few of those. And essentially, this is an attempt to build a sort of a homogenized, climate-ready data set. Not that we're the first ones to ever have done that, but we'll be doing that using NASA models and reanalyses and data assimilation. So that's the new thing here. This is the team. So Emma is the PI, Stephen Paulson, Pam Wales, Brad Weir, and I'm also part of the team, so I'm mildly qualified to give this talk. So we start with a brief description of a few systems that the NASA GMAO maintains and develops. Those are reanalysis type of systems. MERA-2, a lot of people are probably familiar with that. Should I be using this? Or can I use the mouse? Yeah, okay. No, not really. All right. So MERA-2 is a meteorological reanalysis, 50 kilometers horizontal resolution, 72 levels, up to 0.01 hectopascals. And it covers the period of basically the satellite period to the present. One of the things that we do assimilate there is ozone. The plot on the right shows, this is a plot from a validation paper for MERA-2 ozone. It highlights one of the issues that we always face when we try to stitch together different data types. We have this period up until 2004, late 2004, where MERA-2 assimilates as BUV ozone and then switches to MLS and OMI. And the plot shows correlations with data sets in the UTLS. It's basically UTLS kind of partial column ozone correlated with ozone sounds. And you can see there is a change of character here. There is, I would really like to use this. Okay. Yeah, so there's this first period when we have, the correlations are kind of okay, but, you know, drop down sometimes to 0.75 or something. And in the MLS period, we have a better representation of UTLS ozone. All our systems are based on data assimilation. There's a very quick spiel on what data assimilation for constituent does. Essentially, it turns this picture on the left into the picture on the right. We have, in this case, MLS water vapor observations on just collected from one day. And data assimilation is a Bayesian method of combining and propagating observational information from in space and time using the fundamental equations. So essentially, the model is used to propagate this information forward. And in the process, it accumulates data from today, yesterday, 3 days ago, and so on, and builds up this gridded picture of a constituent water vapor in this case. So the second product that we have, and I won't spend much time on this because I have another talk just on this, is M2 SCREAM, stratospheric composition reanalysis of Aura MLS, where we assimilate a bunch of constituents from MLS. The meteorology dynamics is constrained by MERA-2, so we don't re-assimilate meteorology. It uses a full stratospheric chemistry model called StratChem, and it covers the entire MLS period from 2004 to more or less present-ish. And it's validated. There's already a few papers here that use this product. So that's MERA-2 SCREAM. Now, going to SAGE. So if we want to construct a comprehensive, scientifically meaningful climate data set using assimilation and models as transfer standards, and we need to know how those different data sets compare. And this is ozone, SAGE observations compared with MERA-2 ozone at different levels, selected levels in the stratosphere, basically a scatter plot. And it's a very, very good agreement here. This is kind of like the type of thing that we like to see in those cases. Likewise, SCREAM, ozone, MERA-2 SCREAM compares with SAGE equally well. Not surprisingly, both systems assimilate MLS data. When we do this for water vapor, well, the agreement is not as good. So with MERA-2, it's actually quite bad, and we don't actually expect it to be better. We know that it's not just MERA-2, but none of the major meteorological reanalyses represent stratospheric water vapor very realistically. Sean Davis has done some work on that, and if you don't believe me, ask him. So that's what we have for MERA-2. However, SCREAM, which does assimilate water vapor from MLS, the agreement is better. It's not perfect, but it's better. Also, SAGE 3ISS water vapor is quite noisy, so you can expect some sort of scatter here. And as long as it's consistent with the uncertainties that we assume for SAGE, it's okay. So, scientific objectives here. Does the assimilation of, can we assimilate SAGE ISS water vapor? Essentially, that was our question. And the point that Emma made here is that SAGE data is likely suitable for assimilation. I actually didn't believe that going in, because there are so few profiles. There are 30 profiles per day, and I thought that wouldn't be enough to make the assimilation work. And we're actually surprised, because it does work. We'll evaluate the results against independent observations here. So we have the following 3 experiments here going. We'll have a control experiments where we don't assimilate anything. It's still constrained by meteorology from MERA-2, but no assimilation of water vapor. We have SAGE-only experiment where we assimilate SAGE 3 ISS water vapor. And we have an MLS version 5 assimilation. So SCREAM reanalysis assimilates version 4. 4.2, MLS version 5 is slightly different. It's slightly drier. So we'll be comparing those experiments here. And this is the first comparison here. So this is MERA-2 SCREAM on the left, informed by version 4.2 MLS observations of water vapor, and this is this V5 experiment, and this is the difference, and the difference is exactly what we would expect from assimilating those 2 different data sets. Version 5 is a little drier, pretty much uniformly everywhere. So no surprises here. Now, if we do the same for, again, MERA SCREAM on the left, we have the SAGE 3 ISS assimilation and the control experiment, which doesn't assimilate anything, but it still churns things around according to the meteorology. And those are the differences. So in each case, this will be experiment minus MERA-2 SCREAM. And this is after 1 day of assimilation. They look identical pretty much, as we would expect, because there are 30 profiles. Don't really get you anywhere. You have to wait a little longer. And here, hopefully, this is going to play, and it's playing. So this is an animation that's showing the same kind of setup here. So we're subtracting MERA-2 SCREAM from the MLS version 5 assimilation, from the SAGE assimilation, and from the control. And what we see on the left here is just the difference between the two versions of MLS. And here, control is different. But as the time progresses, and this is September, October, November, so a few months of assimilation, first day of each month, we see that this picture here, this difference becomes more like this one, showing that assimilation of SAGE does make a difference and actually brings the field closer to what we expect from MLS. This is not true for high latitudes because there are no observations there, and this is basically an observation count which is kind of uneven geographically. So this is a very encouraging result. We can assimilate sage, which was a big surprise to me, and it actually does have an impact on the fields. Now, if you look at, this is my favorite example, really. This is the tropical water vapor tape recorder from MERA2, which basically has climatological tape recorder. So it's the same thing repeats every year, more or less, starting in the middle stratosphere. Then you have SCREAM. Tape recorder kind of changes here from here. There is interannual variability because of the assimilation of MLS observations. This is the same, but from this MLS version 5 experiment, which will be very similar to that one. And this is the SAGE 3 ISS assimilation experiment, sort of in the early period. And now, what happens when we have, in 2022, the Hanga Tonga eruption? Well, this happens. We suddenly have plenty of water vapor in the stratosphere going up here. And this is very well represented in SCREAM, as expected, but it is also represented in the SAGE 3 ISS assimilation experiment with some delay here. And that delay is, again, no surprise. The system needs some time to accumulate enough information from the data to get this to work, but eventually it does. And but I don't really know how, we're somewhere in October, I think, or September. By September, we have a very similar picture here, at least in the zonal mean sense. So this is incredibly encouraging. There is a bit of delay, and the delay here is, of course, because of the paucity of observations, but also because SAGE 3 ISS observation errors are incredibly large. They're just insanely large in this layer here because of the aerosols and large amounts of water vapor. And of course, in data assimilation, those observations are in some sense weighted by their uncertainties. So this is a picture. Those are comparisons. Top row. Oh, that's a busy plot, and I made it. So let's see. Each panel shows essentially, you have the right-hand side panels that show MLS and SAGE assimilation here in the region of interest in the tropics. So this is for March, April, and May. The left-hand side panels are statistics of the differences. So those are PDFs, essentially. How much time do I have? 2 minutes. Okay, I should be able to do this. Progressively, as we go forward in time, this little, in March, there is not much here in the way of the additional extra water vapor here. But as we go to May, the SAGE assimilation starts developing this kink here. Those are comparisons of SAGE observations with SAGE, with assimilated SAGE. It's kind of similar situation here. In June, comparison with SAGE, between SAGE observations and SAGE assimilation shows that this kink here is quite developed, but it's not quite there. So the question, why it's not there and can we do better? So we just tried to do something very simple. We tried to reduce the observation errors in this layer between 70 and 20 hectopascals for SAGE 2 and see what happens. And we have 2 experiments, and this shows the evolution of water vapor in the experiment that I just showed. And the one with reduced observations gets there faster. And you can even see this kind of staircase sort of behavior here, which comes from the fact that those are observation counts as a function of time. Every time SAGE looks at the right place between 30 south and the equator, the assimilation gets a little bump here and eventually gets to the right point. So that's not something before backup, I guess. How do I go back? Here. Yeah, so in summary, we can assimilate SAGE water vapor, which is a huge surprise to me. And we're not quite there yet. This is, we're tinkering with observation errors and with the setup, but this is a very, very encouraging result. And I think that's where I'll stop.